session with the second lecture by Professor Witt. Please.
Okay, thank you. So, okay, welcome back. So what we have done so far, we had we have P prototype for discrete, for constant discrete, constant. Okay, discrete has no meaning for user. Topics. And then we defined delta P, say on X, on the half space. And so basically it was, we have asymptotics of these types. So we have our U is in that weighted space. So we fix always basically a reference Kuhlmann delta. Yeah? So if you deal with standard boundary problems, this delta is just zero. Okay? And then we just subtract these asymptotic terms to sufficiently many, yeah, as given here by S. I'm not writing, yeah, I just write here a short version of that, and I remind you that we cannot write it like that, but okay, still do. And then we end up in a better space so far as positive. We go down here to regularity 0, but we improve the Kuhlmann order by S. This is what we have done. And actually, there's a well-known example for that. Let me just remind you of the example. So suppose we have U is an H S naught R plus, which means it is an HS on R. It has support in the non-negative reals, and S is positive. For positive S, then we have X minus SU as an output. That's exactly what. So there is no asymptotic term. Yeah, so we improve the Kuhlmann order by S. That is exactly what this multiplication does. And so then we have better Kuhlmann order, but the Sobolev regularity went down from S to 0. Okay, so that is a well-known example. Okay, as I said, so we have now the spaces here, and there are two examples. This is here. Yeah, so that is the way how we have to write the asymptotic terms, not like that, but like, yeah, like shown here. And then the two examples, yeah, if we take the type of Taylor asymptotics, we get back the usual Sobolev spaces, and if we take the empty asymptotic type and Kuhlmann order delta, then we get subspaces. Yeah, and so all what we have done, we have just allowed here a more general Kuhlmann order and other. Okay, so actually there is bad news, but I can show you tomorrow. But this tray space is sort of still too small. We have to enlarge it somehow. We do that tomorrow, and after I've shown you the reason for that. Good. So now we are in a position. Actually, I want to remember that example here. If you have something which is an SP, we take the Manning transform. We get a certain pattern of poles given by P. Otherwise, we are in the Schwarz clause along vertical lines. Yeah, that is the situation. Here you see an example. E to the minus x is certainly Schwarz. The Manning transform is a gamma function that have all these properties. Okay, so now we start to define cone. Yeah, this is the cone calculus. So there's a basically a big cone calculus due to Schulze. An equivalent version is due to Meadows and Mendoza. and I sort of now define an appropriate subcalculus. So there is one big difference for the experts. One big difference if Schulze has a cone operator of order 0, of order n, say A, it is going to take this case as delta to h as minus n as it should be. Here he has delta to the delta minus m. That is due to the factor in front of everything is x, and due to the factor here. So we just change things. That is also true if he has here types p and q. We just change the h as delta p. So p and q are fixed. We have here the same delta. This is one property one observes for boundary problems in the potato model system. Yeah? So we also have here delta, not delta minus m. But this is an essential change just for the experts. Which then explains why certain things later, certain things are different from the general code. So then, as I said, once you have a pseudodifferential calculus, you first have to understand this as a symbolic structure. And the symbolic structure is, of course, we have this inner pseudodifferential principal symbol, which is just, you take here the leading component of that chi here, yeah? So you take the component which is homogeneous of degree m. That's it. And different from the edge calculus, actually, the leading Konomal symbol is a principal symbol in the cone calculus. And this is here that guy, the freeze coefficients at x equals 0. And so we sort of quantize this totally characteristic derivative by I times c. That's like. So if you start with a cone-integrated differential operator, it would be something like that. You have certain smooth coefficients, smooth down to x equals 0. Then these Konomal principal symbol is that one. Yeah, you freeze your coefficients and you replace that totally characteristic derivative by, as I said, I times c. And what you get is a polynomial in z of degree n. Right? So, and for pseudodifferential operators, you cannot expect something like a polynomial, but you would expect something like that behaves like a polynomial, which is then, remember this previous example, which is along these, so after Mellin transform, along these lines, which is in the class Sm. But then it is meromorphic, not just holomorphic. The numbers are holomorphic. Yeah, so that's basically the class we are going to get. So in general, belongs to space M, the order is M, and then we have another asymptotic type, but now not for distributions, but an asymptotic type for operators. We call it R. So the only difference now is that so we have a certain basically pattern of holes. And now basically previously it was allowed to go one direction. Now it is allowed to go both ways. So we have still here this support is still a discrete set of C, subset of C, but now it can go both ways. Yeah? So that is basically it. So actually there is a problem in the pseudodifferential calculus. So we get all wanted properties. So we get composition in the class, we get ellipticity, and so on. With one exception, so there is no good way to fix edge ranks. But this problem already occurs in Potato calculus. So it's nothing new. Actually, now it is more severe. But you want in principle also the cone degenerate operators to be, well, I mean, at the adjoints also to be cone degenerate. And if you basically take the adjoints, then the conormal symbols will sort of reflect things about one of these lines. So everything which goes to the left then becomes going to the right. Yeah, this is simply the reason, yeah, how you have to go both ways. Okay, yeah, okay, then such a principal synthesis is called a Mellin symbol. It's a meromorphic function on all of C, having poles given by R. Basically, it tells us the position of the poles and their multiplicities. And so this condition can be written if you see such an asymptotic type as a non-negative divisor. You take the principal divisor of that form, and this is going to be the lower bound of this is minus R. Which means exactly you can have poles at these positions as given by R, and the multiplicities are as given here. This is marked. And then once you basically cut out the poles, then as I said, so this is going to be classical symbols of order M, classical symbols of order M along these vertical lines. Yeah, so you basically write the Z as beta plus I tau, yeah, and then so it is after this cut off, you get something which is smooth in B and takes values in these M's order. Okay, this is basically the relation we see also here on the previous page. This is just the address point on it. Okay. So then, if the asymptotic type is not that important, we just write here this AS for some asymptotic. Okay, so then here's an exercise. Actually, that's a nice one. The first step is not that easy. So suppose we have here such a Mellin symbol, which just as just said means particularly this. And then basically, once we fix beta, we are along such a line, and then it has a principal symbol. And this principal symbol turns out to be independent of beta. And that's the consequence of the Cauchy-Riemann equation. Yeah, so that's a nice exercise. So basically, you start. So you have these of order M. Then you can write it. This is here again the empty asymptotic type. You can write it as a holomorphic symbol without any pole. And what is left, also asymptotic information is contained here in the second summand. But here we have along those vertical lines, you have symbols of order negative infinity, which is just short things. Okay? So you can just decompose. So this first step is not that easy, but once you have done that step, then you can of course assume here, because this does not have a principal symbol here, you can assume that your symbol is holomorphic, no poles at all, and then you can just use the Cauchy-Riemann equations to see that the principal symbol is independent of beta. So that is basically the next thing. So once basically, if it does not depend on beta, I'm just allowed to write it just like that, because beta plays no role, it just depends on tau. And well, and then thing is, so if that symbol is elliptic, here this Mellin symbol is elliptic in the sense that its principal symbol nowhere vanishes, then just a 1 over H is again a Mellin symbol of the corresponding order, with some resulting asymptotic type. So so remember that the meromorphic functions over any open set in C, they form a field. So basically 1 over meromorphic function is again a meromorphic function. That is not the point here. The point is that you get only in each of these vertical things here, only finitely many poles, okay? And that the behavior along these lines is then with s to the minus f. So why do we get only finitely many poles there? Well, I mean, as the principal symbol is non-zero everywhere, so you're far out. Yeah, once you fix here this stuff, this box here, so far out, the principal symbol dominates, and then this h is going to be pointless invertible. As non-zero, the 1 over h does not produce any new poles out here, and here you get just, yeah? There you have zeros, you get new poles, whatever, yeah? So the elliptic condition, variability in the class is exactly that. Okay? Okay. So, good. So, and why I'm that much interested in the coordinate symbols? Yeah, so I said the leading coordinate symbol is part of the principal symbol, and the principal symbol is a couple, but why I just care about the next order symbols? Because actually, next order symbols depend on the chosen coordinates. I can basically take another x and get other symbols, certain transformation behavior, yeah? So they have no invariant meaning in the sense. Yeah, still why I care that much. And that is because they tell you in which way our asymptotes are mapped by A. Yeah, so it is, but I mean, I've written it in X space, it is easier to see. It can be easier seen in V space or after Melling transform. So basically, what you do is here, you get them by a Taylor expansion at x equals 0. So we have an x to the negative m, and then we get always with each step we get an improvement. Now, so for simplicity, let's assume that. So the m is not important. Let's assume that m is 0. Okay, so then have here our basic weight line. So and the u has certain asymptotics, then we get certain poles here. Okay, and then it goes up this direction. So it's just I make things easy than I just put here and here. It is not the most general case. Just move individual steps to the left. And, well, then basically, after Melling transform, so the first step is, I have m is 0, j is 0. So basically, I just multiply things by h naught. Okay? And this is a meromorphic function. It has an effect that basically kills certain of poles here and adds others. Yeah, it just changes the pattern of poles. That is the effect of this graph. Yeah, of course it also takes effect here and here and here. The next one has an x to the 1 in front of. So the contribution from the next one is basically it changes then, starting from here, it changes asymptotics. And so the next one is the next one. So you get always your only finite contributions, and in the end you get a certain asymptotics. And this is basically completely given as a sequence of coordinate symbols. This is the first step. And then the only thing you need to, for the next step, you have an x to the 1 in front of. Yeah, but I have here the Melling transform of x to the row u. And z is the Melling transform of u plus rho. Just everything. One step to the right, and the next one 2 steps to the right. This gives you, you just need to think a little bit about it. gives you the complete information of all asymptotes you get, and also how asymptotes are altered. So we are really interested in that in that sequence. And basically, this gives us the way to control the asymptotics. Okay. Good. So this will play a role, but it's not hard to prove. If you have basically two contingent operators A and B of orders m and m prime respectively, then the product is a co-degenerate, and the conjugate symbols of order m plus m prime minus L is computed in that way. And here we have this is called the translation product. We have this translation by the order of that symbol. And this sort of comes from the following thing. Here we have one operator, which is x dx. We have an x minus m prime 3x x dx. So basically, what you need to do, you need to commute it through. You need to get that to the other side, and this is then responsible for that shift. That is commuting operation. That is what happens. This is not so hard to verify. Okay. So okay, then next one. So now comes the main step. So we have for say an A with a satisfying the transmission property, we have that result. So this was not in the cone, this was in the edge pattern, so we have the addition parameters y and either, and this was in that form. So the gamma function divided by some other stuff here, a polynomial in either of the J with coefficient solution y. This was the crucial point. So this we need to replace that. So the idea is to get a. I should have said that before. So you wanna. We want to impose boundary conditions, and the boundary conditions basically come from these asymptotic expansions. In order to do that, we have to fix for the right and left side. We have to fix two asymptotic terms. So basically, we want to have operators of that form. So this is not an A plus. It's just general A. With T and S. So we want to have operators doing that thing. Now here we have possibly finding boundary conditions, and here we have possibly finding many co-boundary conditions. We have to kill a co-kernel. So we are, yeah, but the crucial point is to fix here these two asymptotic types, P and Q. Otherwise it doesn't work. That is also one observation where we went beyond the Schulze. So here for edge calculus, he hasn't fixed, right? Did not fix these, and then he has just operators which are non-local operators, sort of order 0 in the boundary, without. So basically, the main point is we want to have these operators gamma pk contained in the calculus. These are local operators. We want this to be part of this T. Yeah, in order to get that, we have to fix that. So therefore, we have to find here the corresponding replacement. But the corresponding replacement is, you see here, there's a family, actually essentially unique, at least what I need to discuss that. Indexed by these asymptotic types, P, yeah, with some fixed delta. Delta is the fixed element, that's important. There are mehrere functions on C with different properties. So the gamma p has poles exactly as given by p. Yeah, so for the class, and R, we said that the principal divisors solid from.
Can I ask?
Yes, sure.
Can I ask again, which is the structure of the entries of the operator? The
I
entries?
come to that. I come to that.
Ah,
This is on the next slide.
sorry.
No, it's fine. It's fine.
But this is like the order Monbel.
Yes. That is exactly the point. So the generalization of a particular model, they replace the asymptotic type coming from a Taylor expansion, x equals 0 by more general asymptotic type. So that's the whole point. Yeah. Now we have here this principal divisor is exactly minus p, which means it has a pole at p of order exactly mp for any p which comes from the asymptotic type, and no other put. And so the gamma function has no zeros. So 1 over gamma is an entire function. We have the same requirement here. And then the gamma function has the property, say, if you have gamma z plus 1, if I do it with integers, then it is easier. It is of order 1. If I have gamma z minus 2 over gamma z, it is, oh man, now I need, hope I get it correct, so it's something like that. There's a symbol of order, but for the poles here, there's a symbol of order -2 and so on. And this we also require here. Yeah, so you shift this here by m, the argument, and then the quotient is of order m. You can also give them exactly this asymptotic type here, that's the second point. Yeah, and so basically we have a choice, so simultaneously for any asymptotic type. We just need it for our asymptotic types we are going to work with, but it just works. Yeah? And here, so if our asymptotic type p is p naught, so Taylor asymptotics, we just take the gamma function. Yeah, so the gamma function has its properties, it's just, so this can be generalized, but this, I'm not going to prove that. Relies on the factorization result of myself. Actually, the first real result I ever proved this factorization. Okay. So then we give a preliminary definition, and we'll just see why things are preliminary. So we just take all, so as now our class, we want to define our class. Psi m delta, and then they have a type. I'm going to say what that is. Yeah, and then it takes p to q and on r plus, and then we have here a number of. Basically, this is our vector bundles over the boundary, if you like. Boundary just consists of one point here. And so we take all operators, two-dimensional operators, so they have economical symbols, such as the economical symbols are, they look like that. It is gamma q, here correspondingly shifted, divided by gamma p, and then some holomorphic factor that the complete order is m, as expected. So why it is the correct choice? No, the delta is just here already contained in P and Q. So it tells you where the asymptotic starts. Okay, so why is the correct choice? Yeah, what I mean, the gamma has poles of exactly order P. So you have a function which has asymptotics of type p. You get okay, I just can't this. We have u. The principal divisor is dominated from below, yeah, it's just component from below by minus p. So now p has the gamma p has the corresponding poles. Then we use gamma p. It is homomorphic. This guy is homomorphic. And then that guy here introduces, reintroduces the correct asymptotic. So there are always the shifts. Yeah, so this guy introduces asymptotics of type Q. That's it. Yeah? So then the first thing, I put it as an exercise, but maybe we do it. At least so that all quantization operators having this common symbols, they form this is close under composition in this class. Yeah, so we have and so wait, what is that? No, that is not too much here. So we have R A has a Q and R, and B is a P and Q, so we just compose C and B. And it's just this. So we have Z plus CN, A, X plus E squared minus L times CB. That was the minus K, sorry. This minus K. This was the rule. So now we just plug in. So K plus K equals L. Then we have a certain AJ. So here things are shifted. What I mean, if I shift holomorphic function in the argument, it stays in that class. So here then we just have, so now the asymptotic types are R and Q. So here I have Z plus M minus J, but then it gets shifted. Yeah, for that I get here plus M prime minus L, J plus K is L, divided by gamma Q, Z plus M prime minus K. Then I get here the BK from the B, and I get here the Z plus M prime minus K, P, Z. And then what happens? It's cancel. So here we state the right thing, and this is holomorphic of the correct order. So they basically are closed under composition. So why I say that it is still incomplete? It is because we write things here in that way. So we have it here, and then all the other stuff here. The problem is here the remainder term, which is green class, which is smoothing operator. But these smoothing operators are given by the mapping properties. And we also want to have that the operators fit that space into that space. Therefore, I have to require this also for the G. And this makes things now a bit more lengthy to write it down. But to fix the Kuhlmann symbols is the basic idea. Okay? So then, okay, so now just now it becomes a little bit technical. But it's too much to say no. But I try to explain here. So I said already in Tielemann's calculus, just let me denote it like this here. B and B and then R plus and there's a type. So and basically the type tells you what sort of local trace operators are involved. So if it's just gamma naught, or maybe I just say this fits into the boundary, this is type 1. If it is d by dn, and then restricted to the boundary, it is type 2 and so on. Yeah? So basically it tells you how many boundary traces you take. And type 0 is what I said before. Just to close the calculus, you have some non-local operators in bound. But actually, you are interested in these local operations. So that is given by the D. And to make things easy, that is not essential. But I have here my basic weight line, and then I just shift them one further to the left. So I just, for simplicity, I'm going to assume that all these lines are free of poles, yeah, for the P. It is not essential, it just makes life easier. Okay, so that is the first requirement. And then we have sort of a first pole. So the first pole, if the first pole is here, everything is fine, but it might be here. Yeah. So then the point is, if you have a first pole, then in order to take these boundary traces, we have to have enough regularity. Also if you have an invertible value, if you would just so in this normal notation is gamma negative 1, before it was gamma 1, but sorry, so it's like yeah. Plus, of course, the C, you need that is larger than 3 over 2. Yeah, as bigger D becomes, as more regularity I need, and I have to control it somehow. So and then basically, so this kicks in at a certain stage. So this is just given by this D naught. The D naught is just defined here as. So here we have basically the distance of the poles to that line. Yeah, and then basically I take the pole which is closest to that. So corresponding D I take, we call it D naught. Yeah, and then basically once the D is larger than this critical D, I have a corresponding regularity I need, yeah, in order to take the traces. We call it SD. And then that is all wrong here. That is so wrong. Oh no, it's not wrong. So here we had a problem. In the edge case, we had a problem with the regularity of the coefficients, but here we don't have a regularity. So in the cone case, this is just a number, and then this is this asymptotic terms are perfectly fine. Yeah, I can just subtract asymptotics in that way, and I do it up to the D here, yeah, up to here, where this is given by that D. And this works if I have enough regularity, if D is larger or equal to this D naught, and if not, yeah, otherwise this sum is empty, then this guy is just here. So and then, so maybe I just write it here. What we get. We have this P, it depends on P, this is still a function of x, it's ux, and we subtract the number of product terms, and so basically as many as given by the P here. Here part P has to be, that is actually all wrong, it must be larger than half. Must be, yeah? And then we have the stuff which is written over. X means not K, and then here we have the traces. This is just this here. Okay, so then basically our calculus looks as follows. So first, we have to define the smoothing operators. The smoothing operators are the green operators. G stands for green. So why do I not write just psi to the negative infinity? The point is things depend on two principal symbols. So if I were to write here this here, delta G and P and Q, this means that it is a pseudodifferential operator of order negative infinity smoothing in the interior. So then there is a compatibility condition between the full symbol in the interior and the conormal symbols, which tells you, the compatibility condition tells you that the conormal symbols of such an A minus JA, they are still there. They have order negative infinity, but they are still there. And in order we want to get ellipticity equivalent to be equivalent to the Fredholm property, which means that operators in the residual class, which is our green class, they have to be compact. And as long as, so basically if the sigma, the leading one, A, is different from 0, then A is in the corresponding spaces is not compact. It is a smoothing operator. Yes, everything is fine. It's locally smoothing away from x equals 0, but it's locally compact away from x equals 0, but it's not locally compact at x equals 0. For that is necessary that its principal symbol vanishes, the whole principal symbol. Okay? And so you see, the order negative infinity leads via the compatibility condition to Lanian symbol or conormal symbols of order negative infinity. But they don't have to be 0. Yeah? Therefore, well, I mean, this is probably not very, I should maybe think about some better notation, but I just put a G here. So, and then what is just the structure? So basically, the KTS will be as it will be later. There's no changes. And the main the main contribution comes here from the A plus G. Yeah? So everything else goes into the green class, and you have to define the green operators correspondingly. So basically, we decompose our U in that way, plus the asymptotic terms, and then basically on that part here, that is here the basic weight function for our, this is a delta, not a t. That's a delta, sorry. The delta, yeah, so we have just smoothing operator with a kernel here in the Schwarz class. Here I write AS for general asymptotic type because we do not control adjoints, but here this takes things to have asymptotics of type Q. And here we get certain coefficients, and we just put here the corresponding Schwarz functions. So this operator has the correct mapping properties, and that is what the G is. Yeah? And it depends actually on the T. Okay. So that is this is one thing. So here I have to change that, and I have to change that. Okay. Okay, so that is one thing, and the other ones are. So the T is just a vector. Yeah, the vector of operators. The T goes from the traces goes from here to here. So we just produce a vector consisting of n plus numbers. And we just do it component-wise. We just that is here the standard L. So that is here the standard basically we do the same thing. That's the inner product. That is our basic space. Yeah? That is also, if you like, this H0 delta any p, and here the length is 0. Yeah, that is our basic space. So here's the inner product. This is something, again, we do not control actual, instead we have arbitrary asymptotic type, and then times here, so these are numbers and the other numbers, and this produces numbers. And that is like, and then we have also the k. The k goes from here to here. These are the potential operators. The potential operators just start with this vector, and then you produce something which is in the space. And the S is in that case just a matrix of the corresponding size. So that is the green class. That is the basically class of complex operators in this class. So now the A is still missing. Okay? Upper left corner was A plus G. The A is still missing, so this is sort of the main contribution where also Kahneman symbols come from. So, and then we just define a corresponding class of, so we take here all, we have this basic weight line, gamma 1/2 minus delta. We allow our dependence on the coefficients. Otherwise, it's just a classical symbol of order n. And then we want, if we just take derivatives at x equals 0, they are of the form as expected, what we need for our Kahneman symbols. Yeah, that is just gives us our Kahneman symbols, this requirement. And so then basically our calculus consists of something in the green class, such operators. And here basically we split things into a behavior close to x equals 0 and a behavior basically actually for bounded x. I said I want to have the operator's Fredholm property, and I also said every singularity or every non-compact exit is controlled by another principal symbol. So now we have here as x equal x goes to infinity, we also have to require something. Because it is not essential, I skip that. But we have actually their third principal symbol. So usually one does is SG calculus, the SG calculus for the x squared. So the A here or the P here has something like that. And we have other choices are possible. Psi P x psi. So this can be controlled by 1 plus psi. So the order is n minus k. And here we have 1 plus x using minus k. That is what one typically does, but other choices are possible. I'm not going to discuss that because we are interested in what happens in close to x. Okay, so and then basically away from x equals 0, we use the standard quantization. We have Fourier transform, x goes to psi, then we multiply by the symbol and then the back transformation. That's the standard quantization, and close to x equals 0, we replace that by this Mellin quantization. Yeah, first the Mellin transform, then multiplication by the symbol, and then the back transform. This is always a pseudodimensional operator. So there are theorems about the equivalence of phase function. This always defines a pseudodimensional operator for positive x, yeah? But it's just at the same time it gives us control what happens at x equals 0. And that's the big advantage if you use a Mellin transform. Yeah, the advantage of the Mellin transform over the Fourier transform in some place. Okay? And then we have certain kind of functions. There is a certain way to localize. Actually, this is a standard way to localize. There's nothing spectacular about it. So actually, here should also be, if you only want to have, so these are the operators in the class where n minus and n plus are 0, if you still have to add a g. Yeah, then we have to add such as operator g. So these are just the operators here in the class where both terms are not there. So that is the code calculus. And then properties. Okay, I'm a bit fast again. Okay, fine. It has the correct mapping property. Yeah, so we start with this HS delta P spaces, and it's mapped into the HS minus M Q spaces. Delta, as I said before, delta stays the same. There's some reason. There's some trick. I don't want to discuss it. So we need. I always had this as a non-negative. Also, this can be relaxed. So in that case, it means that the S has to be at least as M plus, at a maximum of M 0. And if D is at least D naught, then S has to be larger than SP. Yeah, but then we have the correct mapping properties. Then we also have the composition stays in the class. So here, here's an interesting point. Here we have an operator of order of type D, and one of type D prime, and you get actually one of type D double prime, and D double prime is that. There is a formula. This is actually the same formula as in the case of particular model. That tells you how many on traces you take. Maybe I should say it about the time. Maybe I can just add one remark. No, it was. No. There we have, no, what is this here? There it was. Okay, so the type shows up here and here, in G and T, not in A, not in K, not in S. Yeah, that is. Okay, so then, so what is still to be done is ellipticity and the Fredholm property. So first of all, we have a principal symbol space. It is important always to have an intrinsic characterization of the principal symbol space. Then, and here it is, just some notation, factor S. So we have, for the first, here, for that guy, we have something which is homogeneous of degree M. And then for the H, we have the H is, in here, we know the asymptotic type in terms of P and Q. So if I see it as principal divisors, then it's, so I shift the Q by negative M, and then so it was 1 over GP, so here is a minus P. That is not that important, it's just as a formula. Yeah, and then basically both have to be compatible, which means if I take the principal symbol of H, then it depends on tau, and if I take the principal symbol, this principal symbol here, choose x equals 0, then they are equal under that condition. It's just a computation. That's always negative psi. And then there always in the construction of the parametrics, it's always that's the most important thing, that you have this short exact sequence. So you have so the principal symbol map. You have an intrinsically described principal symbol space, which means intrinsically described means it is surjective. Yeah, and if the principal symbol vanishes, you are sort of 1 or better. And this is all what you need for parameter construction. Because, so if you have just, it is the case in any pseudodifferential calculus. So you take the principal symbol, ellipticity, is the pointwise invertibility of the principal symbol everywhere. Yeah? Whatever your principal symbol is. When it's invertible pointwise, you take the pointwise inverses, and then you realize, because you have an intrinsic characterization, that basically the inverses again belong to the class. Well, the principal symbols, you have the inverses, with m replaced by negative m, in our case you have the q and p switch positions, but that's not that important. Okay? So, and then basically, because that is surjective, you find you find an operator having these principal symbols. Let's say the first operator is A, the second operator is B. So by construction, A times B minus identity has a vanishing principal symbol, just by construction. Therefore, you end up here, but these are already compact operators. So at that stage, you have constructed Fredholm parameters. Yeah? You get the Fredholm property, and then by some tricks, you can just improve it to get something in the residual class. But this is so basically this short exact sequence is always the main step. Yeah? So if you don't have it, your calculus is sort of not. You're not done with your calculus. Okay. Good. Let's see. Oh, 4 minutes. Okay. But I have 2 more talks tomorrow, yeah? So then, and so basically, the principal symbols only come from the A, yeah? The important observation is, so G, K, T, S, everything in the green class, that is compact, therefore, it only depends on A. Yeah, the ellipticity and, no, this is wrong, the ellipticity, that is nonsense. The ellipticity is the inverted pointwise invertibility of the principal symbols. And this should be equivalent to the invertibility of A up to the remainder in this residual class. That's 2 different things. But, yeah, okay, so then the operator is elliptic, yes, of course. The principal symbol has to be non-zero everywhere. And the usual ellipticity in the cone calculus is that this is an elliptic. But I mean, sorry, the ellipticity here of that guy via the compatibility condition already implies that this is elliptic. But then in the cone calculus of Schulze and Melrose, the condition is that this basic weight line, gamma 1/2 minus delta, is free of poles, of zeros, sorry, it's free of zeros. Yeah? Here we need a bit more, but this is related to the fact, so Schulze maps the space K as delta into K S minus and delta minus M. And in our case, the delta stays. Yeah, so then actually, so we get something elliptic, we can invert it, and we want it to be holomorphic again. This is a stronger condition. Yeah, so basically, this is holomorphic and holomorphically inverted. This coefficient. So basically, in Gottingen model, this coefficient here, it is just a number. Yes, the A naught is just a number, this number has to be non-zero. And then of course, some condition as x goes to infinity. So, and then we have it. So the following conditions are equivalent. A is elliptic. A seen as such an operator is a Fredholm operator for some S, and then automatically for all S. And also, third condition is A admits a parametrics in the calculus, that there is an operator of the corresponding order, because everything is compact here, so the T placed in a row, you can have T equal to 0, such that we have basically PA minus identity and AP minus identity both are green operators. And this is here just computed what we get here. And if I write P, then it is P, comma P, and here's Q, comma Q. Yeah? So and then as a corollary, we also get spectral invariance. If an operator, as an operator from here to here, is invertible, then the inverse is basically a parametrics in that sense, so it belongs to the calculus, and the type can also be given. is just the things, and I think that. Ah, yeah. Then there's one more. This class is also coordinate invariant. Also, more precisely, if I have different morphism of R plus with a situation at infinity, then this push forward of A is again in the class with the same arithmetic types. So basically, what I do here is so here I have A, and this is just I just take the A. I should be curly A, but it's okay. Yeah, and then I get here a plus and then I get here this. Okay, then I have here, so basically I have a different morphism. I just get it. That is to pull back another inverse. I hope it's the right thing. Yeah? So basically we get coordinate invariance. This will then also be crucial later if we are on manifolds with boundary, so we have coordinate invariant calculus, which is essential. Later here, not in that case, so if you're on a half and then you have sort of the x is fixed, later on it will be essential. Okay, so I think my time is up. Thank you.
Questions? I have a small one, but maybe it's a stupid question, I don't know. All the sublet spaces you introduced and the mapping properties you were studying were L2 based.
Yes.
Are there analogs like LP based
Certainly there are, but we can solve it.
that you put in principle?
Yeah, so if we at some point go nonlinear, we have to do that. But no, we have to basically. Okay, so here it is very nice to have puncture, and one of the other forms therefore. So LP then I guess it is some harmonic analysis becomes involved. That's a lot of work. It's not so my favorite topic.
You defined in a simplified way. You said let's define for integers and relative interpolation, and then but you define some of the space.
Yes.
And of course you gave some formula.
Yeah.
But for here you can do this. You can just say the same.
Yes, of course I can get something by interpolation. Yes.
Relative interpolation, but then of course the interest applies to.
Yeah, but then I mean you cannot work with spaces defined by interpolation, right? You want to have, so if you study some finer properties, you want something like an intrinsic description.
So my remark is that answer to this question.
Yeah, well, of course,
Anyway, but,
yeah, something can be done, yes, certainly, yeah. But this is actually, I don't think that this is actually the things one really want to have. So.
I have a question about in the Cormander calculus, for example, you have one asymptotic expansion for the symbol,
Yeah.
then you have the principal symbol and all the components of order minus n.
Yeah.
Say, give you information on the locality of the operator. This gives you the Wojcicki residual.
Yes.
The operator. So in Montet de Monbel,
Yeah.
I don't remember well, but I think that Fedoso proved the Wojcicki formula.
I think something can be done in that direction. So, but I would, I think if there something has been done, I would check out short. But I'm not sure. So here, so in general, this is about the calculus and no spectral geometry is involved.
So the problem of the index is still open.
Yes. No, but
Are you planning to use the eta invariant example? Eta invariant?
well, I mean, okay, if you do this sort of analysis, yeah, So basically, it falls into two big groups. People are interested in spectral geometry, and people interested in PDEs. And I come from the PDE side. Yeah, so oh, okay, maybe should not. No, I leave it at that.
Okay, then let's read again. Like 10 minutes break.
Estoy en un texto como en el hecho
¿En serio?
No.